Hi, my name is John Vickers. I'm the Principal Technologist for Advanced Manufacturing for the NASA Space Technology Mission Directorate. Over the past year, NASA has worked to establish a strategic framework comprised of 18 technology capability areas linked to specific outcomes and within the context of 4 strategic thrusts: go, land, live, and explore. These technology capability areas are explained by providing an envisioned future priority plan, setting out our future technology development vision and aimed at developing transformative, cross-cutting technologies that enable NASA's missions while also supporting commercial and other government agency needs. The purpose of my briefing today is to provide you with an overview of the advanced manufacturing envisioned future and seek your feedback to further inform, improve, and update our plans and to enable increased participation with our stakeholder community as we help to grow innovation across the economy and begin our partnership on a new science exploration and commercialization journey. I want to mention a few examples of how advanced manufacturing contributes to some of our most exciting NASA exploration missions. Artemis, the Space Launch System, the James Webb Space Telescope, and the International Space Station as examples. Each of the images on this chart illustrates the innovation, advanced technology, and human contributions from advanced manufacturing that enable some of NASA's most exciting products. The Space Launch System, manufactured in NASA's Michoud Assembly Facility and home to our National Center for Advanced Manufacturing, is a marvel of cutting-edge manufacturing technology in every element, including the core stage aluminum cryogenic tanks that are friction stir welded to reduce defects to near zero, and the RS-25 engines that are incorporating additive manufacturing technology to reduce the cost by 50% in the future, and the solid rocket motors that are transitioning from steel to composite cases. You'll hear more about each of these technologies later. The James Webb Space Telescope mirrors are made from beryllium and coated with gold and make 14 stops at different manufacturing sites around the U.S. before they are completed. The International Space Station, one of the first projects that I worked on at NASA, it has been continuously occupied on orbit since the year 2000. We used another NASA-invented welding process to build the modules and have had 20 years of microgravity materials and processes science. I wanted to mention our strategic technology process briefly. For more than a year, we've used the strategic roundtable approach called STAR to collect a diverse set of inputs from our NASA mission directorates and NASA centers and program plans like Artemis, the commercial LEO plans, and decadal surveys. The other connection to be aware of is with our recently released Moon to Mars objectives that form a blueprint for shaping our exploration plans. There are 63 final objectives that cover 4 broad areas of science, transportation and habitation, lunar and Martian infrastructure, and operations. The agency also added a set of recurring tenets to address common themes across the objectives. I'll refer to these connections when I cover the relevant technology areas and gaps. The Principal Technologists and System Capability Leads have prepared highly prioritized envisioned future priority plans covering transformative, cross-cutting technology gaps mapped to specific outcomes. Today, it is for these plans that we are asking the public, government, industry, and academia to review and provide feedback. Starport is the database where the envisioned future priority plan information is displayed in the form of technology gaps that will be used to inform our NASA program investments and budgeting processes. This chart illustrates the overall strategic technology framework and relationships between our top goals to ensure American leadership in space technology. The thrust of Go, Land, Live, and Explore, the 18 outcomes, and the 18 capabilities where the envisioned future plans take shape. It is this set of integrated capabilities that STMD has prioritized to best support the NASA missions that I already mentioned, including Artemis Commercial LEO and the SMD Decadal Surveys, Moon to Mars objectives, and more. The advanced manufacturing capability and envisioned future plan primarily supports the outcome for emerging space industries in the Explore thrust. But as you can see from the asterisk, that is a highly cross-cutting and contributes to many other capabilities and outcomes. The envisioned future plans are a highly prioritized set of technologies and gaps. We're constrained by the limits of funding and time, etc. We can't fund everything. We have prioritized based on criteria such as strategic alignment, benefits, impacts, urgency, and scope, and more. The Advanced Manufacturing Envisioned Future Priority Plan are in priority order on this chart: in-space manufacturing, additive manufacturing, digital manufacturing, and composites. Each of these areas has been thoroughly studied in a multi-month NASA-wide prioritization process to support their greatest impact to the outcomes and thrusts and more. You can see some of the metrics for each of these areas on the chart. We are interested in making NASA's missions more capable and affordable, and how that would be most impacted by closing the technology gap. In my opinion, to close gaps and achieve outcomes is best achieved with an integrated plan across mission directorates and centers, across TRLs and programs and projects, with increased collaboration and public-private partnerships, and leveraging other national strategies and initiatives, some of which are listed here. The most favorable area, the sweet spot to address, since this is advanced manufacturing and emerging commercial space industries, is what's well known as the Valley of Death. The graphic on the upper right is our space technology pipeline, which we plan to work across. The next 4 charts will cover the technology areas and gaps. The format is the same for each. I'll cover some of the motivation, rationale, and state-of-the-art and next steps, future focus areas, and likely investments in my limited time. In-space manufacturing is the number 1 priority in the advanced manufacturing area. It is mentioned specifically in the blueprint objectives related to capabilities in support of continuous human lunar presence and a robust lunar economy, supporting cislunar orbital surface infrastructure, using in-space resources to reduce the mass required to be transported, and systems for reuse and recycling. Think about in-space manufacturing in terms of location and/or an application. What we are doing today on the International Space Station for tech demonstration and commercial LEO development, such as the In-Space Production Applications Program. In-space infrastructure, such as the flagship NASA OSAM-1 and OSAM-2 programs, and the Office of Science and Technology Policy, ISAM National Strategy. Lunar and Mars surface manufacturing, technologies to reduce the mass required to be transported, and systems. The strategy is already working for us with the recent announcement of collaboration opportunity, the ACO, and the Tipping Point Partnerships solicitations, both targeted at in-space and cislunar and lunar surface infrastructure. Some top priority gaps are in on-demand manufacturing of metals, electronic components, recycling and reuse, in situ resource utilization derived materials for feedstocks such as aluminum, for lunar surface manufacturing, and welding in space. 3D printing or additive manufacturing is the most revolutionary manufacturing technology in our generation. It offers powerful design flexibility and dramatic reductions in cost and schedule. It has numerous aerospace applications. I also think it has the most utility for the previous area of in-space manufacturing. It is ideal for applications with very complex geometry. Like in-space manufacturing, it's a very new technology. Large-scale technologies are just being demonstrated. Certification approaches are almost 100% experimental, taking a long time and costing too much. And part variability is still the Achilles heel. You might have seen that we have a solicitation to address one of our gaps for a Space Technology Research Institute on the topic of accelerating additive manufacturing certification and computational tools. We have also identified several areas for future projects and investments, such as advanced modeling and simulation, materials for extreme environments, including refractories for nuclear propulsion, new processes such as additive friction stir and directed energy, and large-scale freeform applications, as well as NDE inspection, in-situ monitoring, and closed-loop control. The digital transformation, digital twins, and artificial intelligence, and other computational approaches are the basis for the fourth industrial revolution and are fundamentally changing the way we work. Especially in aerospace, where the complexity of our systems has significantly outpaced conventional development approaches, we are at a tipping point. This is highly relevant to advanced manufacturing. The European Union, for example, has a strategic initiative called Industry 4.0 for digital transformations in design, manufacturing, and operations. In the US, we have the White House OSTP Materials Genome Initiative Strategic Plan and the National Strategy for Advanced Manufacturing. You'll see a new plan come out on October the 7th, each with a focus on deployment of new materials and manufacturing processes at a fraction of the cost and twice the speed by harnessing the power of computational tools. Today in aerospace, we have limited physics-based computational materials, design, and manufacturing capabilities in use. We primarily use the traditional experimental building block approach for R&D to certification, which again takes too long and costs too much and is a major agency and industry problem. So we're interested in interdisciplinary, model-based everything approaches that analyze, synthesize, and harmonize the links between disciplines into a coordinated and coherent whole. We're interested in the digital twin, physics-based modeling of predictive relationships between processing parameters, materials microstructure, materials properties, and hardware performance, especially in the areas of in-space manufacturing, additive manufacturing, and composites. These technologies will be critical to our future. I already mentioned our Space Technology Research Institute project, but we also have a project for the digital twin of the machined assembly facility, a digital factory. And I have proposed a project for a digital twin of the lunar infrastructure, including power, ISRU, construction, manufacturing, and more. Imagine a virtual command center, a digital twin for our lunar operations. It's the only thing that really makes sense. Composites for spacecraft and other in-space applications is our fourth area. In my opinion, we can achieve an immediate 30% weight savings and even more, and a 25% cost savings compared to the state-of-the-art of aluminum manufacturing that is most widely used today in space vehicle structures. However, composites usage in space applications lags other industries such as aviation and military. The recent decadal survey, Astro 2020, identified composites, materials and processes development and optimization as a key technology for dimensionally stable structures. Thermoplastic composites are not really used today for aerospace structure, but they offer many advantages and development is rapidly advancing. We have projects today, such as an early career faculty solicitation topic for tailorable composite design concepts for dimensionally stable structures, where we just made 2 awards. An early stage innovation solicitation for functionally graded materials for space applications that is under review now, thermoplastics composites for space applications, and adhesive bonding thermosets and welding of thermoplastics, because joints are another Achilles heel. We are also interested in digital and model-based characterization and certification, high-temperature materials and structures, and new materials, and space environmental effects on materials. I'll skip this chart, but it is really intended to show a snapshot of some of the current projects and investments in these areas. I'll finish up with a summary, and I hope you've seen how exciting this area is and that advanced manufacturing technologies are critical to our NASA missions, the nation's aerospace industry, and almost every sector of the U.S. economy. You can find these same areas prioritized in many current national strategies, which, by the way, we have contributed to. I mentioned in the beginning that better collaboration between government, industry, and academia will be key to accelerate the realization and innovation of these technologies. I hope I've been able to articulate an integrated and focused plan for these investment strategies across our full technology readiness level pipeline and across mission directorates at NASA. That's all. Thank you very much.